So we were talking about conduction, right? In the last two classes, we defined or we derived heat diffusion equation, and then we started talking about the boundary conditions, which are of the importance here. I told you whenever you deal with partial differential equations, you have three types of boundary conditions: Dirichlet, Neumann, and mixed. Okay, and you know what are the general forms. We were talking about these few boundary conditions. Just look at this one. What type of boundary condition it is? Dirichlet boundary condition. Okay, why? Because you know what is the unknown in the heat diffusion equation? That is temperature. So if you describe boundary condition in terms of the temperature itself, the unknown itself on any boundary, that is a Dirichlet boundary condition. And if you represent it as a gradient, it means partial T by partial X or something like that, then it would be a Neumann condition. And if you present a combination of both, like partial T by partial X plus some parameter multiplied by T equals something, so that is Neumann condition. But anyways, now see what physics do these boundary conditions represent or depict. If you look at this side, this is 150 degree centigrade, although the heat transfer seems to be one dimensional in this case because the wall is of infinite length. So instead of going towards the upper side, heat is going only in one direction, or heat transfer is more dominant in this direction. But if you look at this side is an isothermal curve or surface, isn't it? Why? Because the whole side is at the same temperature, which is 150. Similarly, this side is 70 degrees centigrade, so it is also isothermal. You understand that? So if I say that some wall is isothermal, so what should you remember? That mathematically you need to describe the same temperature on all the points of that wall, right? So this is what you mean by isothermal. Second condition, this was about the Neumann. I hope I spell it correctly. Neumann condition. And Neumann condition, what? When you describe the temperature in terms of its gradient or let's say derivative with respect to x, y or z. So if you represent it like this, I told you in the last class that this is basically a measure of this thing, isn't it? dt by dx, if you talk about the conduction. So from Fourier law, you know this is the heat flux measure, partial T by partial x. So partial T by partial x is kind of a Neumann condition. If you represent it like this, that instead of presenting it as an isothermal curve, what you say that the heat transfer across this surface, heat transfer rate or flux across this surface is this much. Let's say on this boundary you specify Q naught to be 50 and on this side you specify Q naught to be minus 50. Now if you see these kind of boundary conditions, I am just talking about it from the analytical point of view. If you look at these numbers 50 and minus 50, do you think that there is some kind of energy storage within the volume? If I put the question like this, that what would be the energy storage in this wall, and you have this much heat transfer rate on one side and this much heat transfer rate on the other side, what would be energy storage? It should be zero. Why? Because Q naught, whatever is going in, the same is going out. So that minus sign is there just to represent the outgoing direction of something is coming in, which is kind of positive, and then the other one is going out, which is the negative thing. So you should be able to describe all those mathematical parameters into English or the physics, and then you should be able to translate that English into mathematics. Okay, this is what you call mathematical modeling. But anyways, This is specified heat flux boundary condition. Now there are few other, I would talk about this thing, insulated boundary. I told you that if I ask you that Q dot is equal to 0 on some surface, what do you mean by it? That there is no heat transfer. There is no heat. Now be very careful, because some of the boundary conditions, they are having the same mathematical form but different physical perspective, altogether a different physical perspective. Okay, so be very careful. I am talking about insulated boundary. Insulated boundary means there is no heat transfer across that surface. Now if there is no heat transfer, I can write this thing as this quantity. I hope you understand it. Partial T by partial x at x is equal to 0, and this is an unsteady process, so you can also define T as well, time. Now that is 0. So it means simply you can say partial T at 0 at all the time divided by partial x is 0. Why? Because K is not 0. Okay. Now it means this surface is insulated. Now having this surface as an insulation surface does not mean that you would have no temperature over there. Obviously that surface would carry some kind of temperature. Okay, but Q dot is 0, T is not 0, remember that. Okay, so insulation is 0. This is the derivative which we are putting equal to 0. So remember this thing, that if you are having insulated surface, you need to describe it mathematically like this. So this is a Nyman condition. Partial T by partial x across that surface would be 0. Understood? Okay. Then there is another thing. Just look at it from a different point of view. I say that this is the surface which we were talking about. Let's say this is the surface, this is a wall, there is a point, or let's say I also plot a surface over there, and at the same distance on the right hand side I would also draw this surface. Okay, now this line is in the middle of these two. Okay, now my point is, if this temperature is T1 and this temperature is also T1, would there be any heat transfer across this surface? Not at all. So that means partial T by partial, if this direction is x, partial T by partial x would be 0, isn't it? Across this surface, partial T by partial x would be 0. Now this is kind of the same mathematical representation as you have in insulated boundary condition. But this type of boundary condition, physically it is known as symmetry boundary condition. It is known as what? Symmetry boundary condition. So mathematics is the same. Mathematics is the same, right? But physics is slightly different. Or you can say that if there is some symmetry, it would act as an insulated boundary. If there is a symmetry surface or symmetry boundary, so that would act as an insulated boundary, insulated surface. Okay, so you should understand that. Sorry? If I say, let's say I have this wall, and I say that right in the middle I have a symmetry boundary, right in the middle. And for example, you have this temperature profile on one side. What would be the temperature profile on the other side? Image, isn't it? The same temperature profile at all the distance. Whatever the variation of this one is, the same variation you would have on the other side. Okay, so this is an example of symmetry boundary condition. Remember that. What do you mean by it? Sorry? Yes, that would act as an insulation boundary condition. But mathematically there are two ways you can say to represent it. One, this is the symmetry boundary condition. It means you don't have made it an insulation yourself. It is acting as an insulation surface. right? But to call it as an insulation surface, or let's say if some other boundary condition is being taken as insulation boundary condition, it means that you yourself have put some kind of insulation on that surface physically, right? So that is also a way to have an insulation, like you keep the temperature on both the sides equal to each other, so that would not let the heat transfer from one side to the other. Okay. Right. Now next is the convection boundary condition. Just see, if you have one surface, okay, let me draw it over there again. Let me put it this way. I have this wall, heat is being transferred from here to here. Now I say that on this side you have some fluid moving across it. Okay. Now it means heat transfer on this side would be due to convection. Now if I ask you to define the boundary condition on this surface, I am talking about this surface. If I ask you to define the boundary condition on this surface, remember that surface balance condition, energy balance on a surface. You remember that? I told you that whatever is coming in, the same would be going out. If you have a system, if you have a closed system, let's say control volume type of thing, then there can be energy storage, there can be some kind of energy generation, right? So if you have a surface, you can't store energy in that. You can't produce energy in that, or you one is storage and the other one is what? Generation. Yes. So you can't store it, you can't generate it. So it means if you look at this surface, whatever is coming in from this side has to go out from this side. Now if you see, from this side energy is being conducted, and on the other side energy is being convected. So these two needs to be equal. You understand that? So that's how you put the boundary condition on that surface. Okay. So what do you mean by it? That Q dot conduction, on this surface Q dot conduction equals Q dot convection. Let me write it down over there. What is, let's say if I say that X is equal to L on this side and X is equal to 0 on this side, what is Q dot conduction from Fourier law? You remember that? So that is K minus K A. Area is the same in both the things. So partial T by partial X, and T needs to be L or T, just to make it a generalized thing. T is dependent on L and T, and then you would have what? H Ts minus T infinity, and by the way this S is TL minus T infinity, because L is the surface temperature. At X is equal to L you have surface. Okay, so this is the boundary condition if you have conduction on one side of the surface and convection on the other side of the surface. Okay, so this is quite simple. Now how to use these boundary conditions? More effectively we would use those boundary conditions in numerical, when we look at the application of the numerical techniques, the finite difference method on these type of problems. Okay, we are not going to use these conditions analytically. There may be some phenomena where we can use them analytically, but more dominantly we would be using them for numerical techniques. Okay, we will talk about that I think after like 3 weeks hopefully. Okay, but remember it, very important to understand. Okay. So you can see that this is the convection boundary condition. Heat conduction at the surface in a selected direction, heat convection at the surface in the same direction. Okay, so this is what you can define it from Fourier law for conduction, and this is what you can define it from Newton's law of cooling for convection, right? So if you talk about the radiation, that there is no convection at all, there is no convection at all, but you have some kind of radiation. So obviously the heat which is being conducted to the surface would be going out through radiation. The simple phenomena. Whatever is coming in needs to go out, and it is the physics which would define what mode of heat transfer is being used. Like for example, if you solve any numerical problem from your book, that was the question asked from me, I think twice or thrice, that if you have some data missing in the question, let's say there was no information related to emissivity given in the question, like for example the quiz in the last class, right? So if you see that question and you don't find anything about radiation, there was no mention of it, you can only state one reason, one you can say assumption at the top of the question. Assumption: there is no radiation. You assume that there is no radiation, okay? And it also, you should be able to sense what kind of phenomena. So coming back to my point, this is radiation boundary condition, and you can see that on one side you have conduction. If I look at this side, on this side you have conduction, and on the other side radiation is being emitted by heat is being emitted by radiations, okay? So this is how you can define it mathematically. You remember this principle for a gray body. Okay, there is one more point, that if there is no mention of a gray body in a radiation kind of problem, just assume that it is a gray body. Generally we take that assumption. As engineers, you don't go for let's say the exact answer that you need to have like 13.19876. No, not at all. If you get 12, that is fine, but obviously that 12 needs to become from you can say the originally correct method. Okay, don't say it's a kind of tukka kind of thing. This is not applicable, but you should be approximate these things using fundamental principles. Okay, this is the interface boundary condition. Generally, interface boundary condition is used where you join two surfaces. This is interface. Okay, you join two surfaces, or let's say there are two liquids which are basically on top of each other, just like the sea surface of a water. You see, on top of it there is air, on the lower side there is water, but there is a surface which is kind of playing as a role of interface between two media. Now on that interface, the properties for both of these liquids or both of these two surfaces would be the same, right? Please remember this thing. Like for example, if I say yes, look at this point very carefully. Conduction and conduction. Let's say you are joining two solids. Just like two metal strips. You are joining two metal strips, and let's say this metal strip is having a conductivity of K1 and this metal strip is having a conductivity of K2. But because they are having an interface, so both of them would have same temperature on this surface, isn't it? And similarly, if you apply energy balance principle on this surface, this heat transfer rate should be equal to this heat transfer rate. Do you understand what I am saying? Okay, let me explain it once again. For example, let's say you have joined two metal strips, and this orange line is showing that interface. Okay, for example, this metal strip is having a thermal conductivity of K1, this metal strip is having a thermal conductivity of K2. Now tell me, if there is some temperature distribution on this side, there would be some other kind of distribution on the other side. Let's say it may be like this. It may depend on thermal conductivity. These are just I took few examples. Now my point is, there would be some heat transfer rate in this direction. There would be some heat transfer rate in this direction. Okay, if you have, let's say, T1 and T2, and obviously T2 is taken to be greater than T2. Now my point is, heat transfer rate on this side must be equal to heat transfer rate on the other side. Agreed? Now, what would be heat transfer rate on this side? Minus K1. Let me say this is Ts. Let me say this temperature is Ts. So can I write heat transfer rate on this side equal to minus K1 T1 minus Ts divided by delta X? Let's say this is delta X. Can I say it like this? Similarly, I would put it equal to minus K2 what? Ts minus T2. I'm sorry for that. This is okay, this is minus K Ts minus T2 divided by delta X. Do you understand what I am saying? And Ts remains the same on this interface. It means this is the surface where both of those metal strips are having the same temperature. Why? Because they are being joined on that surface. Okay. So this is how you define an interface boundary condition. Remember this thing. Like for example, if there are two liquids, here you have air and on the lower side you have water. So on this interface, velocity of air should be equal to velocity of water. Temperature of air needs to be equal to temperature of water. This is what interface condition is. And if you look at it from a heat transfer point of view, whatever is coming in needs to go out. Okay, on this side it is being done by conduction, on the other side it is also being done by conduction, but you have two different conductivities, so you can define them mathematically like this. Sorry, T2 what? Okay. 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 Let me simplify it just to make it understand. This is K1 T1 minus Ts, that delta X remains the same, so this is minus K2 Ts minus T2. So this is what needs to be equal. So what is your question?
So K2 and T2 can be different from K1 and T1.
K2 and
T2.
T2 can be different from what?
T1 and K1.
So obviously they should be.
So why can't the Q1 and Q2 be different?
Just look at this interface boundary condition. What is the energy principle for an interface? Interface is just like a surface. Interface is just like a surface. Can that surface store energy? Can that surface produce energy? Whatever is coming in needs to go out. So what does that mean? These two temperatures, this T1 and T2, they would adjust themselves in a way that heat transfer remains the same on the both sides of that heat interface boundary, right? So this is what energy principle is. You can't violate it. Whatever is coming in needs to go out. Is there any problem? Okay. So These are few different types of boundary conditions. Okay, fine. This is okay. Let me solve a very simple form of heat diffusion equation. Let me solve it. What can be the simplest form of heat diffusion equation? Simplest form. If I ask you that I am talking about 1D steady state, no source of heat is involved. That would be what? Partial square T by. Simple as that. Steady state, it means no storage is involved. No source is, it means Q dot G is 0. 1D, it means you just need to take one dimension. Now it means that you are talking about either a wall of an infinite length, or you are talking about a rod where heat transfer is more dominantly in a single direction. Okay. Now generally temperature is a function of x, y, z and t. If I say this is only 1D, so it means these two dependence would be removed, and this time is also removed because of, so it means t is just a function of x. Now can I write this thing as this one? Why? Because now t, that partial sign has been replaced by the differential one. Why? Because now t is only dependent on one variable. This is what ordinary differential equation is. If t is dependent on more than one variables, then you should have gone for the partial sign. So you can see that this partial differential equation has been converted into an ordinary differential equation. Okay. Now let's solve it. How many boundary conditions are required to solve this? Two boundary conditions. What is the order of the derivative? 2. So you can have two boundary conditions, and those two boundary conditions can be in term of what? Temperature or flux, right? So what you can see is, let's say I would call this temperature as T1 and I would call this temperature as T2. You have this ordinary differential equation. Can you solve it? Second derivative is 0. What would be the first derivative? A constant. And for which relation you would have first derivative as a constant? Isn't it? Take its derivative. You can integrate it just like this, like for example dt, and you can just integrate it like this. You would have the same thing. Okay, so you can integrate it and you would have this linear relationship. Is it linear? Yes. Tx equals c1x plus c2. Now c1 and c2, they are what? Coefficients, and those two coefficients are to be determined by boundary conditions. Right? So Tx is c1x plus c2. You see, let's say I take this x and I say that on left side x is equal to 0 and on this side x is equal to L. So what I can call is this t at x is equal to 0 equals what? T1. So that can be taken as x should be put equal to 0. So C2 needs to be equal to T1. Right? Similarly, T at x equals L equals what? T2. C1 x needs to be equal to L. What is C2? T1. So C1 would be equal to what? You understand that? So what is the final form of this? Is, by the way, this is known as a general solution. A general solution, right? And once you put the boundary conditions, this is what? The particular solution, isn't it? You understand it, right? So particular solution for this 1D heat transfer would be Tx equals, I think I should write it over there. Tx equals, what is C1? T2 minus T1 over L x plus T. Do you understand it? So it means if you have a one-dimensional steady state no heat generation heat transfer process, what kind of temperature profile would you have? Linear temperature profile. You would be having a linear temperature profile. Right? Now, let me draw it. This was the wall we were talking about. Let's say the infinite, this is the representation of an infinite wall. This temperature is T1 and this temperature is T2. I ask you to draw this curve. Remember, Tx is equal to what? T2 minus T1. This is what you have. So what kind of curve would you be getting? And where would it start from? This is the intercept. You remember? Equation of a line. And what would be the slope? Understood? If you have any questions about the derivation, or let's say anything conceptual over there. Okay, just to show you the applicability of the other side of boundary condition, which is the flux one, you have Tx equals C1x plus C2. If I say at x is equal to 0, temperature is, for example, T1, and let's say at x is equal to L, you have dt by dx equals 0. This is just a mathematical scenario. What would you do? You would say, now how can you find out that particular solution? Tx equals 0 would be what? C1, and that would be equal to T1, right? Now, what would be the other side of the boundary condition? If you take its derivative, that dt by dx would be what? Sorry, this would be C2. I'm sorry. Yes, this would be C2. So what would be the derivative of this side? dt by dx equals C1. So dt by dx at x is equal to L would be C1. So let's say, what would be this quantity? At x is equal to L, this is 0, right? So now tell me, what is the physical meaning of this mathematical scenario? You have T1, you have an insulation over there, and you have only one dimensional heat transfer. Come on, tell me, what would you get out of it? Yes, that would be a constant temperature. Why? Because you are putting an insulation on the other side. You are putting an insulation on the other side. You have temperature T1 over there. There is only one dimensional heat transfer which is possible. If some heat reaches this surface, it needs to go out. but that is an insulation. And if there is an insulation, would you be having any kind of heat reaching at this point? Not at all. It means all the points on that wall would be having the same temperature, right? So you can see it, like for example, if this thing is, what is C1? C1 is 0. So what would you get as Tx? Tx would be T1. It means that all the x points you have T1. Do you understand it? So once you put the boundary conditions, or you use the boundary conditions, you should be able to look at it from the mathematical point of view, that where are you going, right? Okay, this is just one scenario. Anything else? No? Okay. Let's solve another point. That is case 2. Now case 2 says we have steady state 1D heat transfer. Now what would be the governing equation for conduction? Now see, in this case, can I write it like this? Come on. I can write it like this. Why? Because this is 1D and there is no dependence on time. So if I take its first derivative, that would be equal to Q dot G over K with a negative sign, and you have X. If you take another derivative, this Tx would be equal to minus Q dot G, sorry, X plus C1, there should be C1 as well as a constant. So this Tx would become X square plus C1x plus C2. Yes, X square by 2. Thank you. Now you see, by putting a heat source within that wall, temperature distribution has been changed from linear to quadratic. Do you understand that? Like for example, let me draw it. Yes, this could be the wall, and if I draw it like this, what would be this? It would look like parabola, a curve, quadratic curve. That would not be a straight line anymore. Clear? Now I hope you understand how do you apply the boundary conditions to find out these C1 and C2. Done? Okay. Now this is how you can solve. We are done till this point. We are done with computation of temperature profiles for 1D heat conduction with and without heat source. We are done. Okay, and you know what kind of boundary conditions are also involved. You also know what were the boundary conditions which we talked about. Now there are few other things which you can use to look at the temperature profiles, or let's say the total heat transfer phenomena as far as conduction is concerned. We are just talking about conduction now. Okay. For example, if I say I use the most simplest one again, 1D steady state, no generation of heat, What was the temperature profile? T1 minus T2 divided by L into X plus T2. Okay. Now, let me put it this way. For Fourier law, for Fourier heat conduction law, I would write that heat transfer as minus Ka delta T by delta L, isn't it? If I say that Q dot over yes, delta T by delta L, so I want to look at synonymous to this relation, V equals IR. V equals IR, a popular relation, you remember that, a famous one. What is that? Ohm's law. Yes, Ohm's law. So that Ohm's law thing is there. We want to make it look like this. So this V corresponds to, essentially this is delta V, if you remember. This is V2 minus V1 from your electrical circuit course, right? So this is T1. So if I say this is delta T, and then you would have Q dot delta L over Ka. Can you write it like this? Isn't it? And by the way, this Q dot is what? This is heat transfer rate. This is rate of heat transfer. And I is what? Current. Rate of charge transfer. Okay. So this corresponds to this one. So Q dot corresponds to current. Delta V corresponds to delta T. And you have some resistance as well. This is what? This plays the role of a resistance, right? So can I say that this resistance in a thermal system, this resistance for a very simple system where we are not talking about any kind of heat transfer, any kind of heat generation, and no transient phenomena is involved, can I write this thing as this, the resistance, and I would call this resistance as thermal resistance. Okay, just look at it. You understand this thing? Fourier law of heat conduction. If I have this Fourier law, Q dot equals minus Ka delta T by delta L, and remember those analogies. Q dot is analogous to current. Why? Because one is heat transfer and the other one is charge transfer, rate. Now delta T is responsible for driving the heat, delta V is responsible for driving the charges, and similarly the rest of the parameters would determine thermal, and let's say this is electrical. You understand it? Now let me put it this way. This Q dot V equals IR from Ohm's law. Remember those analogies? So can I say this V is equal to delta T? Essentially it is delta V. So delta T can be written as Q dot delta L over Ka. Just forget about the negative sign. Okay, this is negative or whatever it is. This V1 minus V2 would become V2 minus V1. What is this quantity? Thermal resistance. You understand that, right? Now it means now there is some advantages of this technique. There are some advantages. For example, if I say that this is the rod which you are talking about, this side is at temperature T1 and this side is at temperature T2, you would have some kind of heat transfer over there, obviously you would have some kind of thermal resistance as well. You would have some kind of thermal resistance as well. Now, do you understand this concept? How do you develop the thermal resistance from this very simple phenomena? Remember, you would only use this thermal resistance concept once you have constant heat transfer rate. Constant heat transfer rate, once you have that, and there should be no heat generation as well. The system needs to be 1D. The system should behave in a steady state condition. Steady state condition means constant heat transfer rate, and there should be no heat generation. So if I try to develop this kind of relation for a phenomena where you have heat generation, what was the relation? Tx was minus q dot g over 2k x square plus c1x plus c2. Even if you put the boundary conditions, can you develop a relation synonymous to the Ohm's law from this equation? This is a linear relationship. Remember that this is a linear relationship. Is it a linear relationship? Not at all. It is a quadratic one. So concept of the thermal resistance would come in, or you can use this thing, the concept of thermal resistance, for heat transfer phenomena. If you have one-dimensional heat transfer, if there is no heat source involved in the phenomena, and this system is steady state. Okay, so it means, I repeat my point, you have thermal resistance equals L over Ka. Now, I would more appropriately call it as conductive resistance. If I look at the other side, let's look at the convection. In that case, Q dot is equal to what? HA Ts minus T infinity. This is what? Delta T, and this would become Q dot into 1 over HA. So what would be thermal resistance in case of convection? 1 over HA. You understand that? Now, for example, let me give you an example over there. You have a wall. So let's say this is an infinite wall. This is temperature T1, this is temperature T2, and there is some flow going on this side with temperature T infinity. Okay. Now, if I ask you to develop a thermal resistance network, look at the question. I ask you to develop a thermal resistance network. How would you develop it? Look at this side. Just like your electrical circuit course, on this side, instead of voltage, you have temperature. Then you have this wall, and this wall needs to be represented as what? What kind of resistance? What kind of thermal resistance? Conductive resistance. Okay. So I represent it like this, and I say that this is R conduction. You understand that? And on this node you would have temperature T2, and then there is convection. So you need to add another resistance to represent this R convection, and on this side you would have T infinity. You understand that? So conduction is being represented by R conductivity, and convection is being represented by R subconvection. Now this R conduction is equal to what? And this is what? Now these two resistances are in series or parallel? These two resistances are in series. Now see, can I combine those two resistances and represent it as the same one resistance, L over Ka plus 1 over Ha? And at this side you have temperature T infinity, and on this side you have temperature T1. Now what is the advantage? Tell me, what is the advantage? There is a huge advantage of going towards this approach. Sorry? Yes, exactly. You don't need to have T2. You don't need to have this information of T2. See what we have done. Even if you do not know what T2 is, you can have the whole important information of this system. Okay, now see, you can represent this thing as what? T1 minus T infinity equals Q dot into L over Ka plus 1 over Ha. This is what you have. Like for example, if I ask you to find out heat transfer rate in this system, and you only know what is T1 and T alpha, and you know what are those system properties are, L, K, A and H, you know what are those properties. Do you need to define that T2? Not at all. Now it means you are skipping some kind of boundaries, information on some kind of boundaries by this approach. You can skip them, right? Now similarly, let me put it this way. I have these two metallic strips. On this side I have T1 and on this side I have T2. This metallic strip is having a thermal conductivity of K1 and this one is having a thermal conductivity of K2. And again, because we are just talking about one-dimensional systems right now, so I am taking an infinite wall. Now tell me, you have T1 on this side and you have T2 on this side. What kind of thermal resistance would you be having? What kind of combination? At least you can identify there should be two thermal resistances. You should remember that. So it means, now remember that both of those two thermal resistances, they are having the same temperature difference across them. What kind of resistance combination would be there in an electrical circuit if you have same voltage difference? That would be the parallel combination. Okay, so if you have a parallel combination, voltage difference needs to be the same in an electrical network, but for thermal network, temperature difference should be the same, right? In a series, heat transfer rate should be the same, just like the electrical current needs to be same in series in the electrical resistances which have been placed in series. Now see, now this resistance can be written as what? L remains the same. Why? Because they have the same thickness. Area remains the same. The cross sectional area remains the same. Let's say L over K1A, and this resistance would be L over K2A. Now do you need to have any kind of information about this temperature? Not at all. You don't need to have that information. Now you can see that this heat transfer rate would be kind of Q1 and this heat transfer rate would be kind of Q2. But you can have a combined effect, or let's say a summed up effect by this relationship, where you can say that T1 minus T2 equals sum Q dot. Obviously that Q dot would be a combination of both of these two. Sum Q dot should be equal to what? A parallel combination of L1, L over K1A and L over K2A. You tell me. No, you tell me. You have taken that electrical system, electrical network course, or even if in your physics, if you have two conductivities, just talk about it from a common point of view. If you have two resistances, where would be larger amount of current going? Towards the lower resistance. You understand that? So same is applied to this Q1 dot. Like for example, where would be greater Q1 you can observe? Where would be the greater Q1 going? Q1 dot. With the lower thermal resistance. And it should be having the greater K1. It means thermal conductivity is more, you would have more heat transfer rate. Simple as that. All the things are connecting. Right? So you can have this information, but you don't need to know this temperature at the interface. This is what the purpose is. So similarly, let's take another example. I have this wall, and then I have these two walls, and then I have this one. I only know what are those two temperatures, this temperature and this temperature. Let's say this is thermal conductivity K1, this is K2, this is K3, and this is K4. Come on, how would that thermal resistance network look like? You can just start from the temperature, just like you start from the voltage in the electrical circuit course. You would have one thermal resistance. Why? Because the whole heat transfer rate would be going from this side. Then at this point it would be divided into two. Then they would be joined at this point, and then you would have, so this is what, this is T2. You don't need to know the information of these two sides. Let's say you put them equal to T3 and T4, no problem at all. Even if you don't have any information about T3 and T4, you can solve this system. Done? So this is a topic given as composite wall in your book. Okay. Now similarly, even if with this complex system I add convection over there and you have T infinity, what you need to do? I just add another series resistance where R convection is there, and you can see it is going like this. And then you also don't need to have this T1. You can just go with T infinity if you know it. Done? But this approach is only possible when you have one D heat transfer, steady state, no heat generation. You like it? Okay, we also need to look at the form of the heat conduction equation in cylindrical coordinates. Okay, we have done it for, I would not derive these heat conduction equation. You have that derivation in your book. You can see that I have derived the Cartesian form, and the rest remains the same. Heat diffusion equation, and I am going to talk about the cylindrical coordinate system, cylindrical form. I would just write down the final form of it. This is 1 over R. What are the cylindrical coordinate system, by the way? R, theta and Z. You know that. R is radius, theta is angle, right? And then Z is the length. So 1 over R, partial by partial R, KR, by the way, this kr radius partial t by partial r plus 1 by r square partial by partial theta k partial t by partial theta plus partial by partial z k partial t by partial z plus q dot g equals rho Cp partial t by partial t. This is the cylindrical form. Okay, like for example, if I say that you have a wire and you need to look at the heat transfer within that wire looks like a cylinder body. So it means heat transfer would be more dominant in z direction because this is z, and if you look at the cross section, this is r, right, and this is theta. Okay, now look at it, this one dimensional heat transfer from this equation. In which direction, which term would be more dominant? This one is the more dominant term, most dominant term, right? So these two terms you can neglect, and for example, depending on the steady state phenomena or the transient one with heat generation or without heat generation, partial by partial z k partial t by partial z equals 0. Let's say I'm taking the simplest one. Didn't you get the same heat transfer form? Right? So choice of the coordinate system depends on the shape of the body. Okay. And similarly, you can apply the boundary condition that at r is equal to, let's say, capital R, you have this boundary condition. At r is equal to 0, you have this boundary condition. Okay. So same applies to this PDE as well. Let me write down this spherical coordinate system equation. What are the coordinates? R, theta and phi. You have two angles and one length, and this comes out to be 1 over r square partial by partial r k r square partial t by partial r plus 1 over r square sine square theta partial by partial phi k partial t by partial phi plus 1 over r square sine theta partial by partial theta k sine theta partial t by partial theta plus q dot g equals rho Cp partial t by partial t. Okay, you can see the radial term remains the same. Yes or no? No, I'm sorry. Radial term does not remain the same. Why? Because there are other transformations as well. So you have altogether a changed equation in spherical coordinate. You might have remembered those transformations from your calculus course if you go from one coordinate system to the other. So you can apply those transformations as well on the Cartesian form, and you can transform those equations into the other one. Sorry? And in the next lecture, I hope to cover few thermal resistances related to radial and spherical coordinates, and then I would be talking about heat transfer within the fins. Okay, please solve examples and few questions.